Hello everyone. In the series of revision classes, we have started our chapter surface tension. And in the last video, I have discussed about what is the surface tension, what is its dimension, what is SI unit, and what is the surface energy, and the relation between the surface tension and the surface energy. Now, our next topic is excess pressure inside a liquid drop or curve. Okay. Now, first is excess pressure inside a liquid drop. Just a minute, huh? One. So excess pressure inside a liquid drop. As you know, the liquid drop is spherical in a shape. But how this will be a spherical? So suppose this is the liquid drop, and inside the liquid, the pressure exerted on its wall is excess pressure due to liquid, and outside pressure due to the air column is then external pressure. As we know, the liquid pressure will be greater. That's why it will become spherical. Okay. So the difference in the liquid pressure and the external pressure is called your pressure excess pressure. Okay. You can write it as pressure of liquid minus pressure of external, or you can write it as pressure inside minus pressure outside, or you can write it as pressure at concave side minus pressure at convex side. So for a liquid drop, it is equal to, means the change in pressure is equal to 2 into surface tension by r. R means the radius of the spherical bubble. And for a soap bubble, the excess pressure means the change in pressure is 4 times of surface tension by r. Now see the proof, but proof is not so much important. So I will give a short about the proof. Now consider a liquid consider a liquid drop of radius r. Consider a liquid drop of radius r. Let sigma be the surface tension. In your book, maybe this can be denoted by S or T. Huh? Let sigma be the surface tension of the liquid due to its spherical shape. Due to its spherical shape, there is an excess pressure. There is an excess pressure P inside the drop, that and outside, that and outside. Next, let the drop, let the drop, let the radius of drop increases from r to r plus that r, increases from r to r plus dr under the excess pressure P. Excess pressure P. Now see, suppose that was the spherical drop and it have radius r. So due to excess pressure, its radius is increases by r plus dr. R plus dr. So that was became its surface area. Now consider initial surface area. So what is the initial surface area? As the drop is a spherical in shape, so the surface area of spherical is 4 pi r square. Now the final surface area is 4 pi, and what is the increase in its radius? R plus dr whole square. Now open the formula, you will get r square plus dr square plus 2 pi r dr. Now neglect dr square, as dr square is very small, so we have to neglect it. Okay, neglect dr square because it is very small. It is very small. Okay, now the final surface area will become 4 pi r square plus 8 pi r dr. So the increase in surface area, increase in surface area. What is the increase in surface area? Final surface area minus initial surface area. Final surface area minus initial surface area. So the final surface area is 4 pi r square plus 8 pi r dr, and the initial surface area is 4 pi r square. So 4 pi r square will be cancelled. You will get 8 pi r dr as the increase in surface area. Now we know that surface energy, surface energy is equal to work done by increase in area, work done per unit increase in area, and the surface energy is equal to the surface tension. So if you cross multiply here, so you will get surface energy. I can write as surface tension in the place of surface energy, and increase in area is 8 pi r dr equal to work done. Now we know that this is equation first. We know that work done is equal to force into displacement, and force is written as pressure is equal to force upon area. So force is written as pressure into area. So force is written as pressure into area into, and the displacement is the increase in its radius, that is dr. So P into area is initial area is 4 pi r square and dr. So that was also work done, and from equation first we have also get work done. So from equation first and equation second, from equation first and equation second, both are the value of work done. So P into 4 pi r square dr is equal to 8 pi r dr. Okay, p into 4 pi r square into dr, sigma into 8 pi r dr, sigma into 8 pi r dr. Now dr will be cancelled, pi will be cancelled, 4 to the 8, and 1 upon r term is cancelled. So we will get p is equal to 2 sigma upon r. So that was the excess pressure inside a liquid drop. Okay, so that was the expression for excess pressure inside a liquid drop. Excess pressure inside a liquid drop. Inside a liquid drop. Now come to the next part, that was the excess pressure inside a soap bubble. So we know that soap bubble has two layers. I have told you earlier about it. So excess pressure inside a soap bubble. Excess pressure inside a soap bubble. As we know that the soap bubble has two surface area, you can do the same step again, but in the soap bubble there are two films. Okay, so its increase in surface area is increase in surface area is in the backward. We know that the increase in surface area in normal liquid drop is 8 pi r dr, but it has two surface area, so we can write one more 8 pi r dr of second surface. So the total increase in surface area is 16 pi r dr. So the step prior to this step, you can write it from the previous one. Okay, so consider the liquid drop, if, increase in surface area, final surface area, then we come to this step, that increase in surface area is 16 pi r dr. So work done. So again, surface energy is equal to work done per unit increase in area. Surface energy is equal to work done per unit surface work done per unit increase in surface area. Increase in surface area. So W upon 16 pi R dr, and we know that the surface energy is equal to surface tension, that is sigma, on cross multiply you will get W is equal to 16 pi R dr into sigma. Okay, that was your equation first. Now we know that work done is equal to force into distance, force into displacement. Displacement is increase in its surface, increase in its radius. That means delta R, and the force is pressure into area. Area is 4 pi r square. Initial area will also become 4 pi r square into dr. So work done is equal to 4 pi r square dr. So that was also the value of work done from equation second. Now from equation first and second, from equation first and equation second, we get both the value of work done. So 16 pi r dr sigma is equal to P into 4 pi r square dr. So dr will be cancelled, pi will be cancelled, 4 just 16, 1 r will be cancelled. So you will get from here P is equal to 4 sigma upon r. So remember the soap bubble has two surfaces, so we have two times of excess pressure inside a soap bubble, inside a liquid drop. Okay, so excess pressure inside a liquid drop will be excess pressure inside a liquid drop will be 2 sigma upon r, and excess pressure inside a soap bubble will be 4 sigma upon r. That means the 2 times of liquid drop. Okay. Now consider the three type of liquid surfaces. First one is ligand. Second one is concave surface. Sorry, convex surface. And third one is convex surface. Okay. Pressure outside, pressure of liquid. Pressure outside, pressure of liquid. Pressure outside, pressure of liquid. Now consider first figure. First figure is plane. Second is convex. Third is concave. That was a rise in liquid level. Okay. Maybe they will be in plane surface, they will be in convex surface, they will be in concave surface. So when they will be in plane, if the surface is plane, what it means, if the surface is plane, surface in plane, so the molecule on the surface is attracted equally in all direction, is attracted equally in all direction. So the resultant force, so the resultant force due to surface tension is zero. Due to surface tension is zero. The pressure on both sides is same. The pressure on both sides will be same. Both sides will be same. Now consider the second case in which the liquid pressure is greater than the outside pressure. So in that case, the surface will become the convex. So if the surface is convex, if the surface is convex, so there is a resultant downward force on the molecule. So there is a resultant and downward force on the molecule for the molecule on a surface to remain in equilibrium. The pressure on a liquid side must be greater than the pressure on outside. And in the third case, to remain the molecule in equilibrium, so the outside pressure will be greater than the liquid pressure. So that's why the figure will become a concave. Okay. So if the surface is concave, if the surface is concave, there is a resultant force F. There is a resultant force F due to surface tension on the molecule. Due to surface tension on the molecule. For the surface molecule to remain in equilibrium, for the surface molecule to remain in equilibrium, the outside pressure must be greater than the inside pressure. The inside pressure. Okay. The topic was ended. Now next is your angle of contact. Angle of contact. Next topic is your angle of contact. So what is the angle of contact? It is defined as the it is defined as the angle theta between the tangent to the liquid surface, tangent to the liquid surface at the point of contact, at the point of contact and the solid surface inside the liquid, and the solid surface inside the liquid, inside the liquid. Now consider the three jar. So the liquid can be raised in three surfaces. First is your concave surface, second is your convex surface, third is your plane surface. Angle of contact is the angle between, if I draw tangent and the liquid surface is this, so the angle between the tangent to the liquid surface and the solid and the solid surface. Now if I draw a tangent this, and this is a solid surface, so the angle between liquid surface and a solid surface is known as the angle of contact. Now in this case, the angle is always perpendicular, that means 90 degree. So in a plane it is 90 degree. In convex it is greater than 90 degree, and in concave it is always less than 90 degree. Okay, wait, huh? That is not equals to, that is theta greater than 90 degree. That means it is an obtuse angle. So that is known as the angle of contact, the angle between the liquid surface and the solid surface. Solid surface means the surface of the jar is known as the angle of contact. So for concave, For concave or convex, and for plane. We have three cases. We know that for concave, theta is less than 90 degree. That means theta is obtuse, and theta is greater than 90 degree. So wait, sorry. Theta is acute here. Theta is obtuse, and for a plane surface, if theta is equal to 90 degree, so theta is perpendicular. So that was the cases. Now come to the next topic, that is your capillarity, and the last topic. Okay, so next topic is your capillarity. What is the capillarity? The Latin word capilla means hair. Capilla means hair. So a tube of very thin hair like core is called a capillary tube. A capillary tube. Now suppose this is the liquid filled with water. Now if you dip a capillary in it, so what will happen? The rise, there is a rise in liquid level inside a tube. So this phenomenon is known as capillarity. Just so see the condition. If I dip a tube which is open from both the end, so there will be the rise in the liquid level. So this is known as the capillarity. Okay. So the phenomenon of rise or fall of rise or of a liquid, fall of a liquid in capillarity tube, in capillarity tube, in comparison, on comparison to surrounding, on comparison to the surrounding, is called capillarity. Okay. Suppose that rise will be h from the liquid surface. So what is the value of h? So h have the value 2 sigma cos theta upon r rho g. Okay. So 2 sigma cos theta r rho g will be the rise in capillarity. So rise in capillarity is H equal to 2 sigma cos theta upon r rho g, where sigma equal to surface tension, theta is angle of contact, r is the radius, rho is density, radius of tube, g is acceleration due to gravity. Acceleration due to gravity. So the topic surface tension is ended. Now I am discussing only the important question of surface tension topic. I will cover fluid chapter in another video. Only this videos will consider of surface tension only. Now come to the first question. Previous year questions. So your first question is, give the expression give the expression for the excess pressure in air bubble. For the excess pressure in air bubble, air bubble inside the liquid, inside the liquid. Okay. Remember one thing, only the soap bubble has excess pressure 4 times of surface tension of upon r, remaining all the maybe it will be air bubble, maybe it will be a normal liquid drop, so all have the same expression, that was 2 sigma upon r. Only the soap bubble has 4 sigma upon r as an expression, remaining all have the expression of 2 sigma upon r. So p inside minus p outside for air bubble is 2 times of sigma upon r, where sigma is surface tension and r is the radius, where sigma is surface tension and r is the radius of that air bubble. Okay, now come to the next topic. What next question? What is angle of contact? What is angle of contact? So the angle I have taught you earlier, the angle between the tangent to the liquid surface and the solid surface the surface of the jar or a container is known as the angle of contact. So of contact, the angle between the angle between tangent to the liquid surface, tangent to the liquid surface at the point of contact and solid surface inside the liquid is termed as the angle of contact. Is termed as angle of contact. Now come to the next question. Next question is also given as the given expression for the excess pressure in air bubble inside the liquid. Same question repeat again. Now next question is give the expression. This chapter only contains a short answer type question and very short answer type question. There is a no long answer type question from that chapter. Okay. Now the next is give the expression. Give the expression for the excess pressure for the excess pressure in a soap bubble in a soap bubble in air. So we know that soap bubble has an excess pressure. Only the soap bubble has excess pressure 4 times of sigma upon r. So the P inside minus P outside for the soap bubble is 4 times of sigma upon r, where sigma is surface tension and r is the radius. Surface tension and r is the radius. Now come to the next question. Next question is why are the drops why are the drops and bubbles spherical and bubbles spherical. So the drop and bubbles are spherical due to the surface tension. So we have studied it that the soap, the bubble, the surface tension of a liquid tends to have minimum surface area, tends to have minimum surface area minimum surface area for a given volume for a given volume. The surface area is minimum for a sphere. The surface area is minimum for a sphere is the minimum for a sphere. Hence, raindrop are spherical in shape. Hence, raindrop are spherical in shape. Hence, raindrop are spherical in shape. Now come to the next question, and the last question of that topic is Magnus effect. Maybe this topic also come in the excess pressure of a fluid, because this is based on the concept of airs, air pressure outside and inside. So what is the Magnus effect? That was very important for your exam point of view. Magnus effect. So remember this question. The difference in the velocities, the difference in the velocities, in the velocities for air results in the pressure difference, in the pressure difference between the lower and upper phases, between the lower and the upper pressures, between the lower and upper phases, and there is a net upward force, net upward force on the ball. This dynamic lift due to spinning is called a Magnus effect. It's called a Magnus effect. Mhm. Now the next question is, what is surface tension? Sorry, explain surface tension and surface energy. Explain surface tension and surface energy. And surface energy. I have discussed both the topic earlier in the video. Firstly, the surface tension. So you can write this in the definition of surface tension. The property of a liquid surface to remain in its minimum area is known as the surface tension. Okay, so that was equator theta plus or it is a property by virtue of which the free surface of a liquid at rest behaves like an stress membrane tending to contract so as to occupy minimum surface area. So this is the definition of surface tension. Next, you can write the formula of surface tension. The surface tension is denoted by sigma T or S. Okay, sigma T and S. And the formula of surface tension is force per unit length, means force upon length. SI unit of surface tension is Newton per meter, CGS unit is dyne per centimeter, and the dimension of surface tension is mt minus 2. Now, second one is your surface energy. So, what is surface energy? You can, if you want, then you can write the some of the example of surface tension. The raindrop are spherical, needles supported on water surface. Small mercury drop are is droplets are spherical, and large burst tends to flatten. Next, hair of painting brush cling together when taken out of the water. Next, oil is spread on a cold water but remain as a drop on a cold water, hot water. Now come to the next one, the surface energy. Surface energy is the energy possessed by the molecule of a surface film of a unit area compared to the molecule in its interior is called the surface energy. Or you can simply write it as the equal to the work done in increasing area of surface film. Okay, so if you want to write in a simple, so you can write this definition. If you have a problem to learning problem in learning the definition of surface energy, so you can learn this definition that it is equal to the work done in increasing surface area increasing surface area of surface film by the unit amount. Okay, the surface energy is defined as the work done per unit increase in area. SI unit is joule per meter square, and you can write also its dimension. So its dimension is same as the surface tension mt minus 2. So it has same dimension mt minus 2. Or you can write it as, because surface energy is equal to the surface tension, so you can write its next SI unit as Newton per meter, or CGS unit as its dyne per centimeter, or dyne per centimeter, or you can write it as erg per centimeter square. So both are the CGS unit of the surface energy. Because surface energy equal to surface tension, that's why I have written it as Newton per meter, and it has same dimensional formula as surface energy. Okay, so you can write these both definition in that question. Now the next question is, derive the relation between surface tension and surface energy. Derive the relation between surface tension and surface energy. Derive the relation between surface tension and surface energy. That was the most important question. Okay, surface tension and surface energy. One of the important question from this is the excess pressure inside the soap bubble, and anything has come. Any bubble is come, air bubble, water bubble, or any type of means creature will become. But if there will be a excess pressure inside the soap bubble, so only it is equal to the force sigma upon r. Rather, all the bubble have excess pressure 2 sigma upon r. And next important question is this: the surface tension and surface energy, relation between the surface tension and surface energy. Most important question of that topic. Okay, I have proved it earlier. So see the topic once again. Relation between the surface tension and surface energy. So we have considered a rectangular frame ABCD in which the wire AB is movable. So when we dip that rectangular frame in the soap solution, so film is formed. When film is formed, which is pulling AB downward, AB downward. Why this is pulling? Due to the surface tension, and the property of surface tension is to minimize its surface area, so it is pulling it downward. But if we apply a force and we increase its distance from x to delta x plus delta x by taking this wire AB to the position A dash B dash. Okay, so what will happen? The change in surface area will be initial surface area minus final surface area. So we will get 12 delta x, and work done in stretching the wire is force into delta x. And we know that the surface tension is equal to force per unit length. So we can write force as the sigma into L, surface tension into length. So the work done is 2 sigma L upon del x, and the change in surface area is 12 del x. Here considered the soaps, we have considered the soap solution has two surface area. So that's why the force applied by both the surface area.
So that's why I have multiplied it by 2. So the increase in surface area is work done per unit. Surface energy is work done per unit increase in surface area. So work done is 2 sigma L del x, and the increase in surface area is 2 L del x. On cancelling, we will get surface energy is equal to the surface tension. Okay, so that was the important relation. Okay, from your exam point of view. So this question is very important, and this question Magnus effect is also important. Next, excess pressure in the soap bubble and excess pressure inside the air bubble. Okay, so that's all in this chapter. If you have any doubt or any query relating to this chapter, so you can send that doubt or question to sir or ma'am. They will forward me and I will provide you solution. So that's all for today.